Hi, everybody. I'm Navid. I'm from EDF Research Institute. It's a EPFL-affiliated research institute. It's completely devoted to research on AI, somewhere in the Swiss Alps. And I'm going to talk about today about natural language processing, the bias that's in data, and we're going to go through some story about these two elements. Very soon. OK, so the story today has 3 episodes. But before then, I'm going to ask you some questions. Let's get to know each other. Who is working here on the business side of AI, deep learning, machine learning? Please raise your hand. I'm not, by the way. Who is working more on development side of AI algorithms? Perfect. Who knows what Märzen is? Märzen. That's a beer. That's an important thing to know. It's a part of talk. So that's a Bavarian, Austrian beer. You should try that in the days that you are in Vienna. OK. So the first part of the talk is about basically deep learning challenges that most of you going to be very familiar with that, but we're going to be in the same space and same literature. Then I will talk about word embedding and specifically about word-to-vec algorithms, especially for people who want to know more about the technical aspects of deep learning and the natural language processing. It's full of intuition, so if you are not very much into computer science and algorithms, don't worry, everything is about intuition, so you can get that, which is fun. And at the end of the talk, in the third episode, I'm going to talk about gender-based quantification. It's a recent research that we are doing in EDF, and I'm going to share it with you. So let's go through the first part. What is deep learning? It basically comes from, so the first 2 slides are really boring, by the way. Deep learning is basically based on the neural networks, and neural networks are nonlinear functions. So we have here x, which is the input. We have a set of weights and hidden units and nonlinearity here. And at the end, we have y, which is our class, for example, for prediction or regression or something like this. And what we're going to try to measure is the train based on maximized likelihood. So we want to maximize the likelihood of y given this x, which is the data, and theta. And we usually do all of this stuff with a set of optimization, very basic optimization algorithm like stochastic gradient descent that is pretty known. And what's deep learning now is that deep learning is that to calculate this overall function, we use a composition of functions. So we have this very basic function that we had in neural network. We compose them with a bunch of new and innovative algorithmic and architecture, and we create a much bigger parameterized space that we call it deep learning. And then we have these interesting algorithms like scans and dropout and LSTM and so on and so forth. And whole of this community, this deep learning structure, which is based on the data, is backed up by large data sets and larger computational resources, and a lot of enthusiasm, as you can see, for example, today here from academia and industry, both of them. So it's amazing time to be working on deep learning and knowing about that because of many applications that's bringing into our society and our work. Language and speech processing, computer vision, self-driving cars, or back on door, and information systems like search engines and recommendation systems, and even goes to medicine, astronomy, and energy science. Is completely finding its way into finance prediction, for example, and it's indeed very interesting time for studying and knowing about this interesting tool, deep learning. Though there are also other aspects of deep learning that we should take care of. And in this conference, actually, there are many interesting talks about some of these aspects. So safety and security, uncertainty, which is basically what we know that we don't know about the data, the answers that we know that we can't answer that, which is also another very important part of deep learning. interpretability and fairness and transparency and the data and model ownership, who is the owner of the model, who is the owner of data. Resource consumption, that is actually an important part, is the global warming. And bias, which can happen in data, end user, annotator, algorithm, and so on and so forth. What we're going to talk about today is about just this one, bias that happens in data, and we're going to look at what happens when we bring this data that has bias into natural language processing. I'm going to show you an example. You can find a lot of them. So Farsi is a language that is gender neutral. So yesterday, the problem is right now, you can just try it also on your phone if you know Farsi. I wrote 2 sentences. The first says that which is he or she. So because Farsi is a gender neutral, so the pronoun that at the beginning I have highlighted is a gender neutral pronoun. And both of them are the same. You can see that mudir and khadmatkar ast, which is translated into he and she, and he is related to manager, and she is related to maid. So I didn't do anything. I just put it into this application that you know which is, and that's the result that I get. And the reason is that data that's trained based on that, this automatic machine translation system is biased. We're going to look at that, and we're going to talk how we can measure and quantify this bias that exists in data. And it's a serious issue. So imagine that maybe you would be fine with that, although it really hurts. But if it goes to a job recommendation system, that's definitely going to go somewhere else that you would not like to go. Let's decompose a very basic neural machine translation architecture, and you see something like this, that I'm not going to talk about that. What I want you to notice here is based on the input and output of that is something that's called word embedding. It's a representation of word, and we're going to talk about that a lot. So almost every neural NLP system has a crucial building block, which is called word embedding, the representation of words in a high-dimensional space. We can't, on this talk about all of the bias that exists in natural language processing on all of the systems, but we're going to talk about this crucial component, word embedding, and see whether we can quantify an ethical bias exists into word embedding. Did I say what word embedding is? No. So let's just get a bit warming up with some technical things. So word embedding is a representation of every word in a high-dimensional space. It's very much connected to representation learning, if you're familiar with that. And there we actually represent every word with a D dimension, and every dimension of that, every value in there, loosely reflects a concept in language. When you train a word embedding and then you just project it into 2-dimensional space as we have here, you see this cloud of words. So you can see this is a language that you put it into cloud, and each of them are words. And interestingly, if you look at the clusters that exist here, you see some kind of semantical relation around the terms. And that's a very specific and interesting characteristic of word embedding. So here we see bunch of countries, we see months here, we see some disciplines, and we see some words here that are all about learning. And they are also moving. And they also have subclusters that, for example, going, and gone is here, and flying in here, and drive is here, and so on and so forth. So we have this different granularity of the clusters in the word representation, and we use this word representation almost in all of the NLP applications. It's a very hot topic. You can see the peak of the embedding during the last year, and it's interesting that it's not very updated graph. And the way that is in general it works is that you have the corpus, you have the word embedding black box. It's a kind of algorithm. And at the end, for every word, you have a representation in a D-dimensional space. What we're going to do in the second episode of the talk, we're going to go look at a famous word embedding algorithm. We look at this black box. We get to know each other. We get to know this word embedding algorithm. which is called Word2Vec, a neural-based word embedding algorithm. If you are not a fan of algorithms, don't worry. A good algorithm should be very intuitive and should, by heuristic, you should understand that. If you don't like the formulas that's going to happen here, I'm just warning you. Just skip that. Don't look at them. It's going to be also slides with graphs and many, many different things that just pick up what you like. That's just my point. OK. Don't worry. Relax. Going to be fun. So let's go for Word2Vec. Before we talk about Word2Vec, we should talk about the heuristic that's behind that. And there's a quote from Wittgenstein. Of course, we should talk about Wittgenstein because we are in Vienna, that in most cases, the meaning of a word is its use. It's actually very basic of the philosophy of the deep learning that we are now working, that we don't go and define things, but we try to look at the usage of the things and bring the meaning out of that. So we look at the data, we look at the usage of the concepts, and we bring the patterns that inside of that outside. And although that time there were no computer science, but this philosophy is actually very much related to the deep learning and machine learning and database and statistical oriented approaches. After then, Firth says that you shall know a word by the company it keeps. So you may don't know the meaning of a word at all, but just look at the company that it has, the words that surrounding, and then may you understand the meaning of the word. Does it make sense at all? If it makes sense, we're going to do a game. I'm going to show you a word, and you tell me what it means. Don't look it up. Now I'm going to show you the words that are in this context, that accompany that. What could it be? An alcohol, yeah, it's a beverage. It's an alcoholic beverage. It's from corn, OK? Now I'm going to show you something that you may know, Märzen. And then look at the words that are surrounding with that. It's a bottle. It's a drink. It's alcoholic. It's in bar. It's also bitter. So you can see that between Tesquino and Märzen, the words that are around that accompany that there is a shared space. There is something common between them. And that's the intuition, that algorithmic intuition, that we create word embedding based on that. So Tesquino is a Mexican beer. It's a corn beer, actually. And we can kind of understand that there is a relation between Tesquino and Märzen. And both of them are about beer, and both of them are about alcoholic beverage. So there is a semantic relation between them, and the intuition is that two words are related when they share many same context words. OK, let's pick this intuition and go to computer science world. We want to have a recipe for creating a word embedding with neural network. We design our favorite neural network architecture. We loop over training data, and training data is a word W and context word C, word like Tesquino and context word like drink, because you drink Tesquino. You calculate a scary thing called probability of context word given the word. You optimize the network to maximize this likelihood probability, and then you repeat it many times. And don't worry if you didn't understand anything. There are going to be figures coming next. So that's the Word2Vec architecture. We see just a very simple one-layer neural architecture. We have a linear activation. We have two sets of matrices. We have the words matrix here, and we have context word matrix. All of them are in this dimension D. We have a trained sample. It says that Tesquino and drink. So drink happens in the context of Tesquino. We have a one-hot encoder here. We pass it through our favorite network. We do a forward pass. We have a probability here. And this probability is actually probability of drink given Tesquino. That's the probability that we are really interested about that. And we just backpropagate and optimize all of your network till we reach this word matrix, which is actually our word embedding. That's it, basically. How does it work? You can imagine that you start the word embedding of a couple of words here in the space. They are randomly started. Tisquino at the beginning is here. Mertzen is at the beginning here. It's just randomly started. It's a toy example just to understand what's going on. We want them at the end to be in the space closer to each other. As you can remember, like the country, they were closer to each other. Here we want to have these two things that are conceptually related to each other close in the embedding space. How can we do that? We have also a set of context vectors that I showed them here with rectangles. We have drink. That is a context vector. And we can get rid of the rest. And what happens is that Tisquino should step by step get closer to drink. Mertzen also should get closer to drink. And at the end of the day, they should end up in the position that's in the spaces closer to each other. How does it happen? We have the training sample of Tisquino and drink. And we start to update the vector to maximize the probability of drink given Tisquino. If you are familiar with neural networks, you know that you usually use a softmax, which has a very tough and big and too expensive normalization over all of the vocabulary that we have. The innovative part of word-to-vec algorithm is that it's very efficient and effective. And it changed the probability of C given W to probability of Y is equal to 1 given W and C. What does it mean exactly? We want to compute what is the probability that co-occurrence of two terms is a genuine probability, is a fine probability. So whether Tisquino and drink are a genuine probability. The point is that the space of language is very sparse. What does it mean? It means that if you just randomly pick two words, of course, our bias, our minds, and we cannot take something randomly. But if you randomly pick two words, the probability that they co-occur meaningfully co-occur with each other is almost 0. And that's the meaning of sparseness of language. The probability that two things happen with each other because we have a very structured way of thinking is very, very low. And that's what we want to measure. And to measure that, we want to contrast this probability from a set of negative samples. So we call the co-occurrence of Tisquino and drink a positive sample, a thing that we're really interested about. And then we select a couple of negative samples, and we try to distinguish these two ones from each other. So it's kind of like a binary classification algorithm, if you are familiar with that. On one point, you have the good samples, the training samples, the positive samples, and on the other hand, you have the negative samples, and you want to separate these two ones together. And that's the way that a clustering algorithm, an unsupervised algorithm, turns to be actually a supervised algorithm. So to say, classification algorithm. And the optimization that we do here is that we try to increase the probability of these positive samples that we observe that into our corpus, observe that into language that we are using. And then we have these k-negative samples that we decrease the probability. We say that they are the ones that we don't like them at all. And we increase the probability of positive samples. They are the ones that we always want to have more of them. That would be the objective function of this negative sampling, that on one part, it has the training samples, that's the positive part, and negative samples that are the negative parts of the objective function. And optimization goes through this algorithm. So coming back to the shape that we have here, these figures, we have this Tisquino and drink. That's our training sample. That's what we want them to get closer to each other. We sample here two negative context words. what we're going to do is that we do the optimization in a way that they get close to each other and they get away from each other. If you understand this algorithm, or you have an heuristic or intuition about that, for sure you are really genius. The paper that's written here, there was 2 other papers after then just to explaining what happens in this paper. But whole of the idea is that we want to have, in an unsupervised way, words that are semantically related to each other, close to each other. Now, given this algorithm, what happens when the data has bias? So we're going to come back to the question at the beginning, start our third part of the talk, and see when you use such an algorithm based on the data that inherently has bias, how this bias is actually encoded into the algorithm. Your words now are different. It's not about medicine and beer and Tesquino. It's about different jobs. They start randomly in a space. There's nurse, housekeeper, and manager. They're just 3 words. And there are also context words in the language, like she and he. If the corpus that you train your word embedding is based on has a lot of co-occurrence of she with housekeeper and she with nurse, and on the other side had a lot of co-occurrence of he with manager, what happens for the algorithm is that nurse and housekeeper start to get pulled through she. And on the other side, manager is start to go through he. I mean, the algorithm itself is innocent. It just finds the patterns that happens in the data. But happens that these patterns are ethically biased. And what happens at the end is that nurse and housekeeper and she going to make some clusters around each other, and manager and he going to have a cluster each other. And when you push this word embedding that you have into, without touching that, into a neural translation model, you're going to see the example that I just showed you in the first slides. What we did very recently is that we tried to measure the amount of bias that, for example, exists in a text. Specifically, we were interested into Wikipedia as a very generous resource of knowledge. We did it for 350 occupations. We created a Word2Vec based on the English Wikipedia, and we measured 2 things: female factor that exists inside every job, and the male factor. As you can see, the green ones are the ones that are actually feminine or masculine, like a waitress. So that's totally fine that waitress is biased through female factors and not male factors. But there are also these red ones, like housekeeper, that is by itself is a neutral word. But when we measure the amount of bias, ethical bias, that exists into housekeeper based on Wikipedia, a fantastic resource, we see that, for example, housekeeper is a word that is very, very, very highly biased and inclined to female factors. Means that the way that we think and the way that our language is connects housekeeper to female. And it hurts. So for a conclusion, we talk about 3 different parts. We talk about the challenges in deep learning. We talk about data bias in natural language systems. We get to know Word2Vec algorithm and semantic word in natural language processing. And at the end, we talk about bias quantification, and we showed the gender bias quantification on Wikipedia. Thanks very much.
Thank you, Navid. Thank you so much for this wonderful and very important talk. And now it's time for a bit of questions. We do have a bit of time. Let's take 2 questions. You can pick out of these 3 that we have from Slido. And for those of you who have not been here before, please use always hashtag AIC18 in Slido to ask questions, and then choose the white box stage. This is the white box stage. Also, the session is not over yet, so if you're not in a complete hurry, please don't leave yet until the Q&A is over. So which one would you like to answer?
So I go for the first one because it's got 2. So this context words, I didn't, thanks for really asking this question. So you have a big corpus, and you start from the beginning of this corpus. You have a window around every term. Like define this window as 5 terms before then and 5 terms after then. And the co-occurrence of every of them would be a training sample. And you start moving from that. So you really need a big corpus like hold a Wikipedia for creating these training samples. And then you're going to have a lot of training samples to train your neural network.
Next question.
I knew that this question was going to come. I don't know if you have time about that, the second one. The decreased influence of bias. So the story that I told you doesn't have a very happy ending story. And the answer is that I don't know. But another answer is also that you can do algorithmic debias, which I'm not very fan of that. What I think that's more interesting is that you quantify the amount of bias that exists in a system. You report that, and as it is an ethical bias, it needs human insight. It needs other disciplines inside to decide whether they want to keep this bias or they don't want. So what I think that's more of my responsibility about that is the reporting the amount of bias and the amount of problem that exists there. The decision, in my opinion, should be by human, whether it wants to have that, whether it wants to decrease that or increase that. Yep.
Yep,
Do we have
great. No, I think that's now, unfortunately, time. But if you have any more questions, please contact Navid or find him going around in this room or outside, and please answer questions. So thank you again. That was Navid Rekabsaz from EDAP Research Institute. Thank you.